Hello there. Tonight, we are going to explore the most relaxing galaxy facts to help you fall into a deep, restorative sleep. You've been bound to Earth for your entire existence, your feet on solid ground, your eyes limited to what atmosphere and distance allow. But tonight, you're going to step back, far back, until the planet becomes a pale blue dot, until the sun is just one star among billions, until you can see the whole spiral structure of our galaxy turning slowly in the darkness. The Milky Way has been rotating for over 13 billion years, and it will continue for billions more, utterly indifferent to human concerns, to your worries, to the small anxieties that kept you awake. Out here, in the cosmic perspective, everything becomes quiet. The scale is so vast that urgency loses all meaning. Let yourself drift now into that immense silence, into the slow, patient turning of our galactic home. The Milky Way is a barred spiral galaxy, a vast pinwheel of stars, gas, and dust rotating around a common center. It contains somewhere between 100 and 400 billion stars. The exact number is uncertain, hidden by dust and distance, and measures approximately 100,000 light-years across. To cross from one side to the other, traveling at the speed of light, would take 100,000 years. Light that left the far edge of our galaxy when humans were just beginning to create cave paintings is only now reaching the opposite side. The scale defies comprehension. And perhaps that's the point. You cannot hold the Milky Way in your mind all at once. You can only glimpse it, piece by piece, fact by fact. Each one a small window into an immensity that puts all human experience into perspective. Our entire recorded history, every empire that has risen and fallen, every person who has ever lived, all of it has occurred in the time it takes light to travel a tiny fraction of our galaxy's width. Our solar system resides in a minor spiral arm, called the Orion Arm, about 26,000 light-years from the galactic center. We're in the suburbs of the galaxy, far from the crowded, energetic core where stars are packed densely and supermassive black holes lurk. Out here, stars are more spread out, the neighborhood is quieter, safer. The nearest star to our Sun, Proxima Centauri, is over 4 light-years away, a distance so vast that our fastest spacecraft would take tens of thousands of years to reach it. We live in a cosmic countryside, a peaceful region where stars have room to breathe, where planetary systems can form and evolve without constant disruption from nearby stellar neighbors. This isolation has been a gift, allowing Earth to develop life, to nurture complexity, to give rise to consciousness that can now look outward and comprehend, however imperfectly, the galaxy that contains it. The Milky Way rotates, but not like a solid disk. Different parts rotate at different speeds, a phenomenon called differential rotation. The Sun and our solar system orbit the galactic center at approximately 515,000 miles per hour, completing one full orbit every 225 to 250 million years, a period sometimes called a cosmic year or galactic year. The last time our solar system was in this position, dinosaurs had not yet evolved. The next time we complete an orbit, Earth will be unrecognizably different if it still exists at all. Yet from our perspective, this motion is imperceptible. We don't feel the galaxy rotating beneath us any more than we feel Earth spinning on its axis or orbiting the Sun. We are passengers on multiple cosmic carousels, nested wheels within wheels, all turning at speeds that would be catastrophic if we could somehow step off, yet all feeling perfectly still because we move with them. The visible band of the Milky Way that stretches across our night sky is actually our view of the galaxy's disk from inside it. We're looking edgewise through the spiral arms, seeing the combined light of billions of stars, too distant to resolve individually. Ancient cultures saw this luminous band and created myths to explain it. A river of light, a path for souls, milk spilled by a goddess. They didn't know they were seeing their own galaxy from within, but they recognized its beauty, its mystery, its importance. On a truly dark night, far from city lights, the Milky Way is stunning. A river of stars flowing across the sky, punctuated by dark rifts where dust clouds block the light of stars beyond. It's a reminder that we live inside something vast, that our perspective is limited, that there are structures and scales we can only glimpse, never fully see. The galactic center, hidden from our view by intervening dust clouds, is a region of intense activity and extreme conditions. At its very heart lies Sagittarius A, a supermassive black hole with a mass approximately 4 million times that of our Sun. This black hole is relatively quiet now, not actively feeding on large amounts of matter, but it's there, an invisible anchor point around which hundreds of billions of stars orbit. Stars near the galactic center are packed so densely that the night sky on a planet in that region would be ablaze with stars, thousands of them bright enough to cast shadows. But the radiation, the gravitational interactions, the sheer chaos of that environment would make life as we know it unlikely. We are fortunate to live far from the center, in a region where the galaxy is gentle, where stars are spaced widely enough to allow for stability and peace. The Milky Way is not alone. It's part of a small cluster of galaxies called the Local Group, which contains about 80 galaxies, most of them small dwarf galaxies orbiting the two dominant members, the Milky Way and the Andromeda Galaxy. These dwarf galaxies are being slowly consumed by the Milky Way, their stars stripped away by gravitational tides, absorbed into the larger structure. This process is ongoing, has been happening for billions of years, and will continue for billions more. The Milky Way is growing, very slowly, by cannibalizing its smaller neighbors. It sounds violent, but on cosmic timescales it's gentle, inevitable, the natural evolution of gravitationally bound systems. The dwarf galaxies don't resist. They can't. They simply dissolve, their stars becoming part of the Milky Way's halo, their identity lost, but their matter preserved. The spiral arms of the Milky Way are not fixed structures, but density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. Stars move into and out of the spiral arms over millions of years, like cars entering and leaving a traffic jam. The arms appear bright because the compression triggers star formation, and young, massive stars are extremely luminous, lighting up the regions where they're born. But the individual stars don't stay in the arms. They drift through, continue their orbits, and eventually move into the spaces between the arms. The spiral pattern persists, even though the stars creating it are constantly changing. It's a pattern made of motion, a structure that exists not in any fixed collection of objects, but in the flow of matter through space and time. Our galaxy contains vast clouds of gas and dust, the raw material from which new stars form. These molecular clouds can be enormous, containing enough mass to create millions of stars. Yet they're so diffuse that if you were inside one, you might not even notice. The density is incredibly low by terrestrial standards, a better vacuum than anything we can create in laboratories on Earth. Yet over millions of years, gravity slowly pulls these clouds together, creating denser regions that eventually collapse to form stars. The process is slow, patient, operating on timescales that make human lifespans seem like eye blinks. A molecular cloud might exist for tens of millions of years before forming stars, and the stars it creates might shine for billions of years more. The galaxy is in no hurry. It has all the time in the universe. The Milky Way's halo, a roughly spherical region surrounding the disk, contains some of the oldest stars in the galaxy, organized into globular clusters, dense, spherical collections of hundreds of thousands of stars. These clusters formed in the early universe over 12 billion years ago, and they've been orbiting the galactic center ever since, following elongated paths that take them far above and below the galactic disk. The stars in globular clusters are ancient, metal-poor, relics from a time when the universe was younger and simpler. They're survivors, having outlasted countless generations of more massive stars that burned bright and died quickly. Looking at a globular cluster is looking at the past, at stars that were already ancient when our sun was born. The Milky Way is also filled with dark matter, an invisible substance that doesn't emit, absorb, or reflect light, but whose presence is revealed by its gravitational effects. Dark matter outweighs all the visible matter in the galaxy by a factor of about 6 to 1. It forms a massive halo extending far beyond the visible disk, providing the gravitational scaffolding that holds the galaxy together. Without dark matter, the Milky Way would fly apart. The outer stars are moving too fast to be held by the gravity of visible matter alone. Dark matter is one of the great mysteries of modern astrophysics, a reminder that what we can see is only a fraction of what exists, that the universe is stranger and more complex than our senses can directly perceive. The sun's motion through the galaxy is not a simple circle. It also oscillates up and down relative to the galactic plane, crossing through the disk approximately every 30 million years. Some researchers have speculated that these crossings might correlate with mass extinction events on Earth, as passage through the denser regions of the galactic disk could disturb the Oort cloud and send comets plunging toward the inner solar system. The evidence for this is debated, but the idea is haunting, that our position in the galaxy, our slow oscillation through the galactic plane, might influence the history of life on Earth, that cosmic geography and terrestrial biology might be connected in ways we're only beginning to understand. The Milky Way is approximately 13.6 billion years old, formed not long after the Big Bang itself. It has witnessed the evolution of the universe from a hot, dense state to the cool, structured cosmos we see today. The galaxy has grown through mergers, has formed billions of generations of stars, has created the heavy elements necessary for planets and life. Every atom in your body heavier than hydrogen was forged in the core of a star or in the explosion of a supernova, somewhere in the Milky Way, sometime in the past 13 billion years. You are made of stardust, not metaphorically, but literally. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stars that lived and died before the sun was born. You are the galaxy contemplating itself, matter organized into consciousness, capable of looking outward and recognizing its own origins. And so tonight, as you feel yourself beginning to drift, imagine floating above the galactic plane, looking down at the Milky Way spread out beneath you. The spiral arms glow softly, traced in the blue light of young stars and the red light of nebulae. The central bulge is a warm yellow, packed with older stars. The whole structure rotates slowly, majestically, a pinwheel of light turning in the darkness. You can see our sun if you know where to look, just one star among hundreds of billions, unremarkable, average, yet precious because it's ours, because it's the star that made life possible, that made you possible. The galaxy doesn't know you exist. It doesn't care, but it contains you, has nurtured you, has provided the elements and the time and the stability necessary for consciousness to emerge. You are part of it, a brief pattern of organized matter, here for a moment in cosmic time, then gone, your atoms returning to the galaxy to be recycled into future stars, future worlds, future possibilities. Let that perspective settle over you now. Let the immensity of the Milky Way, the patience of its rotation, the depth of its time, let all of that carry you into sleep. The galaxy will still be turning when you wake. It turned before you were born, and it will turn long after you're gone. You are safe in its vastness, held by its gravity, part of its story. Rest now, in the quiet neighborhood of stars, in the cosmic countryside where our sun makes its slow orbit. The Milky Way is home, and home is vast, ancient, and utterly indifferent to your worries. Sleep now. The galaxy will take care of the rest. The Milky Way is not alone in the darkness, just 2.5 million light-years away. Close by cosmic standards, though the distance is still incomprehensible by human measures, lies the Andromeda Galaxy, our nearest large galactic neighbor. On a clear, dark night, far from city lights, you can see Andromeda with the naked eye, a faint smudge of light in the constellation that bears its name. That smudge is the combined light of 1 trillion stars, photons that have been traveling through the void for 2.5 million years, since before humans existed, since before our genus evolved. You are seeing Andromeda not as it is now, but as it was in the deep past, looking backward through time with nothing but your eyes. Tonight, we turn our attention to this great neighbor, to the galaxy that will one day merge with our own, to a structure so vast and so distant that contemplating it induces a kind of peaceful vertigo. Andromeda, also known as M31 or NGC 224, is a spiral galaxy much like the Milky Way, though somewhat larger. It spans approximately 220,000 light-years across, more than twice the diameter of our galaxy, and contains roughly 1 trillion stars, compared to our few hundred billion. If you could see Andromeda's full extent in the night sky, it would appear 6 times wider than the full moon, a vast ghostly spiral dominating the autumn sky. But most of the galaxy is too faint for our eyes to detect. We see only the bright central core, a fraction of the total structure. Telescopes reveal the rest: the graceful spiral arms, the dark dust lanes, the glowing star-forming regions, the halo of globular clusters surrounding the disk like a swarm of ancient fireflies. Andromeda is approaching us. While most galaxies in the universe are receding due to cosmic expansion, Andromeda is moving toward the Milky Way at approximately 250,000 miles per hour. This is not expansion. This is local motion, the gravitational attraction between two massive galaxies overcoming the general expansion of space. In approximately 4.5 billion years, Andromeda and the Milky Way will collide, or rather, they will merge, their stars and gas clouds interpenetrating, their structures disrupted and eventually combined into a single, larger elliptical galaxy that astronomers have whimsically named Milkomeda. But this collision will not be violent in the way we usually think of collisions. The stars are so far apart that actual stellar collisions will be extraordinarily rare. The galaxies will pass through each other like two clouds of gnats, their individual members rarely touching, but their overall structures completely transformed by gravitational interactions. The merger will take billions of years to complete. The galaxies will approach, pass through each other, separate again as their momentum carries them apart, then fall back together, oscillating several times before finally settling into a new configuration. During this process, gas clouds will collide and compress, triggering intense bursts of star formation. The night sky on Earth, if Earth still exists, if the Sun hasn't already expanded into a red giant and consumed the inner planets, will be spectacular, filled with the light of two galaxies merging, with brilliant new stars being born in vast numbers, with tidal streams of stars pulled from both galaxies by gravitational forces. But any observers witnessing this spectacle will see it unfold over millions of years, far too slowly to perceive motion in a human lifetime. The collision will be majestic, transformative, and glacially slow. Andromeda has a complex structure with multiple components that reveal its violent history. The galaxy has a double nucleus, two bright concentrations of stars at its center, suggesting that it may have consumed another large galaxy in its past. The collision would have disrupted Andromeda's structure, sending ripples through the disk, but over billions of years, the galaxy has settled back into a spiral form, though the double nucleus remains as evidence of the ancient merger. Andromeda is a cannibal, having grown large by consuming smaller galaxies, and it continues to do so. Several dwarf galaxies orbit Andromeda, slowly being torn apart by tidal forces, their stars stripped away and absorbed into the larger galaxy's halo. The disk of Andromeda is warped, not perfectly flat but twisted, with the outer regions tilted relative to the inner disk. This warping is likely caused by gravitational interactions with its satellite galaxies, particularly M32 and M110, two dwarf elliptical galaxies that orbit close to Andromeda. These satellites are being destroyed by their proximity to the larger galaxy, their stars pulled away by tidal forces, but in the process, they're also affecting Andromeda's structure, pulling on the disk, creating the observed warp. It's a reminder that galaxies are not isolated, static objects but dynamic systems constantly interacting with their environment, shaped by gravity, by collisions, by the presence of neighbors. M32, one of Andromeda's most prominent satellite galaxies, is a compact elliptical galaxy that appears to be the stripped core of a much larger galaxy that was consumed by Andromeda. It's one of the densest known galaxies, with stars packed far more tightly than in typical elliptical galaxies. The outer regions of the original galaxy were torn away by tidal forces during close passages to Andromeda, leaving only the dense central core. M32 orbits very close to Andromeda's disk, and its gravitational influence may be responsible for some of the structure we see in Andromeda's spiral arms, creating ripples and distortions as it plows through the disk every few 100 million years. Andromeda contains a supermassive black hole at its center, much like the Milky Way, but Andromeda's black hole is larger, approximately 100 to 230 million solar masses, compared to the Milky Way's 4 million. This massive black hole is currently quiet, not actively accreting large amounts of matter, but it's there, an invisible anchor point, its gravity influencing the orbits of millions of stars in the galactic core. Stars very close to the black hole orbit at tremendous speeds, whipping around the central mass in just a few years, their motion a testament to the extreme gravitational field they're navigating. These stars are living on the edge, in a region where space-time is significantly curved. where the rules of physics become strange and relativistic effects become important. The spiral arms of Andromeda are traced by bright blue stars and glowing pink nebulae, regions where new stars are being born from collapsing clouds of gas and dust. These star-forming regions are similar to those in the Milky Way, the Orion Nebula, the Carina Nebula, but seen from outside, from a distance of 2.5 million light-years. Each of those pink smudges in Andromeda's arms is a stellar nursery, a place where gravity is pulling matter together, where protostars are igniting, where planetary systems might be forming. There could be planets around those stars, and on some of those planets, there might be life, perhaps even intelligent life. Looking back at the Milky Way and wondering about the possibility of life around our sun, we are looking at each other across the void, separated by distance and time, but connected by the same physical laws, the same cosmic history. Andromeda is surrounded by a halo of globular clusters, dense spherical collections of old stars. The galaxy has approximately 450 known globular clusters, compared to the Milky Way's 150 or so. These clusters orbit the galaxy in elongated paths, some reaching far out into the halo before falling back toward the disk. The stars in these clusters are ancient, over 10 billion years old, formed in the early universe when galaxies were just beginning to assemble. They're survivors, having outlasted countless generations of more massive stars. The globular clusters will survive the merger with the Milky Way, will continue orbiting the combined galaxy, carrying their ancient stars into the distant future. Andromeda also possesses an extended stellar halo, a diffuse cloud of stars surrounding the main disk that extends for hundreds of thousands of light years. This halo is composed primarily of stars stripped from smaller galaxies that Andromeda has consumed over billions of years. The halo is faint, difficult to detect, but it contains a significant fraction of the galaxy's total stellar mass. Studying the structure of this halo reveals Andromeda's merger history, showing the tidal streams and debris fields left behind by past collisions. Each stream is the ghost of a dwarf galaxy, torn apart and spread across the sky, its stars now orbiting Andromeda individually rather than as a coherent system. The light we see from Andromeda left the galaxy 2.5 million years ago, during the Pliocene epoch on Earth, when early hominids were just beginning to use stone tools, when the climate was warmer and sea levels were higher. The photons have been traveling through empty space ever since, crossing the void at the speed of light, never slowing, never stopping, until they finally reach Earth and enter a telescope or strike a human eye. In that sense, looking at Andromeda is time travel, seeing the galaxy not as it is now, but as it was in the deep past. The galaxy has changed in those 2.5 million years. Stars have been born and died. Gas clouds have collapsed and dispersed. The structure has evolved, but we won't see those changes for another 2.5 million years, when the light carrying that information finally reaches us. Andromeda also possesses an extended stellar halo, a diffuse cloud of stars surrounding the main disk that extends for hundreds of thousands of light years. This halo is composed primarily of stars stripped from smaller galaxies that Andromeda has consumed over billions of years. The halo is faint, difficult to detect, but it contains a significant fraction of the galaxy's total stellar mass. Studying the structure of this halo reveals Andromeda's merger history, showing the tidal streams and debris fields left behind by past collisions. Each stream is the ghost of a dwarf galaxy, torn apart and spread across the sky, its stars now orbiting Andromeda individually rather than as a coherent system. The light we see from Andromeda left the galaxy 2.5 million years ago, during the Pliocene epoch on Earth, when early hominids were just beginning to use stone tools, when the climate was warmer and sea levels were higher. The photons have been traveling through empty space ever since, crossing the void at the speed of light, never slowing, never stopping, until they finally reach Earth and enter a telescope or strike a human eye. In that sense, looking at Andromeda is time travel, seeing the galaxy not as it is now, but as it was in the deep past. The galaxy has changed in those 2.5 million years. Stars have been born and died. Gas clouds have collapsed and dispersed. The structure has evolved. But we won't see those changes for another 2.5 million years, when the light carrying that information finally reaches us. Andromeda has been known since ancient times, visible to the naked eye as a faint smudge, but its true nature was not understood until the 20th century. For centuries it was thought to be a nebula within the Milky Way, a cloud of gas glowing in our own galaxy. It wasn't until 1925 that Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, identified Cepheid variable stars in Andromeda and used them to calculate the distance. The result was shocking. Andromeda was far outside the Milky Way, a separate galaxy, an island universe in its own right. This discovery transformed our understanding of the cosmos, revealing that the universe was far larger than anyone had imagined, that the Milky Way was just one galaxy among countless others, that the scale of creation was almost incomprehensibly vast. The merger between Andromeda and the Milky Way is inevitable, written in the laws of gravity, but it's also so far in the future that it feels almost abstract. 4.5 billion years is longer than Earth has existed. It's longer than life has existed on our planet. It's a timescale that makes all of human history, all of recorded civilization, seem like a brief flicker. And yet, the process has already begun. The two galaxies are already falling toward each other, already locked in a gravitational embrace that will end in merger. The future is determined, but it will unfold so slowly that no individual, no species, no civilization will witness more than a tiny fraction of the process. Triangulum, also known as M33, is the third largest member of the local group after Andromeda and the Milky Way, and it orbits Andromeda at a distance of about 750,000 light-years. Triangulum is a smaller spiral galaxy containing perhaps 40 billion stars, and it too will likely be involved in the eventual merger, adding its mass to the final combined galaxy. The three large spirals of the local group are gravitationally bound, their fates intertwined, destined to eventually combine into a single massive elliptical galaxy billions of years from now. And so tonight, as sleep draws near, imagine standing on a planet orbiting a star in Andromeda, looking back at the Milky Way. From that distance, our galaxy would appear much as Andromeda appears to us, a faint spiral, beautiful and distant, slowly rotating in the darkness. An observer on that hypothetical planet would see the Milky Way as it was 2.5 million years ago, would have no idea that humans exist, that Earth exists, that consciousness has emerged in this corner of the universe. They would see only stars and gas, structure and light, a galaxy among galaxies. And perhaps that's comforting, the knowledge that we are not the center, not the point, just one small part of a vast cosmic story that includes trillions of stars, billions of galaxies, and timescales that make our brief lives seem like quantum fluctuations, here and gone in an instant. Let that perspective carry you into sleep now. Let the image of Andromeda that great spiral turning in the darkness, that future partner in cosmic merger, settle over you like a blanket. The galaxies are falling toward each other, slowly, patiently, inevitably. But tonight, they are still separate, still distinct, still beautiful in their isolation. Rest now in the space between galaxies, in the quiet void where light takes millions of years to cross. Andromeda is there, waiting, as it has been waiting for billions of years, as it will continue to wait for billions more. And you, safe in your bed, on your planet, in your galaxy, can sleep knowing that the universe is vast, ancient, and utterly indifferent to your worries. The galaxies will take care of their slow dance. You need only rest. Galaxies are not static islands, floating serenely through space. They move, they interact, they collide. And when they do, the results are among the most spectacular phenomena in the universe. Vast structures warping and merging over hundreds of millions of years. Stars flung into new orbits. Gas clouds compressed into brilliant bursts of star formation. Supermassive black holes spiraling toward each other in a gravitational waltz that will end in merger. These collisions are not violent in the human sense. No explosions, no destruction, just the slow, inexorable reshaping of structure by gravity. Tonight, we witness these cosmic encounters, these trillion-year dances that transform galaxies, that build the universe's largest structures, that remind us that even on the grandest scales, nothing remains unchanged forever. Galaxy collisions are surprisingly common in the universe's history. In the early universe, when galaxies were closer together and space was more crowded, collisions were even more frequent. Most large galaxies, including the Milky Way and Andromeda, have grown to their current size through mergers by consuming smaller galaxies and incorporating their stars and gas. The process continues today, though, at a slower rate as the expansion of the universe spreads galaxies farther apart. But within galaxy clusters and groups, where galaxies are gravitationally bound and not receding from each other, collisions still occur, still reshape the cosmic landscape, still create the beautiful disturbed structures we see through our telescopes. The antennae galaxies, located about 45 million light-years away in the constellation Corvus, are one of the nearest and most studied examples of colliding galaxies. Two spiral galaxies, NGC 4038 and NGC 4039, began their collision about 600 million years ago and are now in the midst of a spectacular merger. The collision has pulled long tidal tails of stars and gas from both galaxies, streams that extend for hundreds of thousands of light years, giving the system its distinctive appearance that resembles an insect's antennae. These tails are made of stars that have been gravitationally flung from their home galaxies, now orbiting in the space between the two cores, destined to eventually fall back and become part of the merged galaxy. The collision between the antennae galaxies has triggered intense star formation. When the gas clouds from the two galaxies collided, they compressed, and compression triggers gravitational collapse, which leads to the birth of new stars. The antennae contain thousands of young star clusters, some containing millions of stars, all born in the last few 100 million years as a direct result of the collision. These clusters glow brilliantly in ultraviolet and visible light, their young, massive stars burning hot and bright. The collision has created a stellar baby boom, a burst of star formation far more intense than what occurs in isolated galaxies. But this burst will be temporary. Once the gas is exhausted, once the merger is complete, star formation will slow, and the resulting elliptical galaxy will be relatively quiet. Its star-forming day is largely behind it. Within the antennae, astronomers have identified over 1,000 superstar clusters, regions where star formation is so intense that millions of stars are being born in volumes of space just a few light-years across. These superstar clusters are similar to the globular clusters that orbit the Milky Way, but they're much younger, still embedded in the gas and dust from which they formed. Many of these clusters will eventually disperse, their stars drifting apart, but some will survive to become the globular clusters of the future merged galaxy, carrying forward the memory of this collision billions of years into the future. The mice galaxies, NGC 4666A and NGC 4666B, are another beautiful example of interacting galaxies, located about 290 million light-years away. Like the antennae, these two spiral galaxies are in the process of merging, and the collision has pulled long tidal tails from both galaxies. The tails are narrow and well-defined, resembling the tails of mice, hence the name. These structures are temporary, existing only during the collision process. Over the next few 100 million years, the tails will dissipate, their stars falling back toward the merged galaxy or escaping into intergalactic space. The mice give us a snapshot of a particular moment in the merger process, a frozen frame in a movie that spans billions of years. When galaxies collide, the supermassive black holes at their centers eventually merge as well, though this process takes much longer than the merger of the galaxies themselves. As the two galaxies spiral together, their black holes sink toward the center of the combined system, pulled by a process called dynamical friction. But as they get closer, the merger slows. The black holes need to lose orbital energy to finally merge, and this energy is transferred to nearby stars, which are flung away at high speeds. This process is slow, and the final merger of the black holes may take billions of years. When they finally do merge, they release an enormous amount of energy in the form of gravitational waves, ripples in space-time that propagate outward at the speed of light, carrying information about the merger to distant observers. The merger of supermassive black holes is one of the most energetic events in the universe. When two black holes, each containing millions or billions of solar masses, spiral together and merge, they convert a significant fraction of their combined mass into gravitational wave energy. These waves were predicted by Einstein's general theory of relativity, but were not directly detected until 2015, when the LIGO Observatory detected the merger of two stellar mass black holes. Since then, dozens of black hole mergers have been detected, though the mergers of supermassive black holes from galactic collisions have not yet been observed. They produce gravitational waves at frequencies too low for current detectors. But future space-based detectors will be able to observe these events, will listen to the universe's most massive objects colliding and merging. Not all galaxy collisions result in mergers. Sometimes galaxies pass through each other and separate again, their structures disrupted but not combined. The collision still triggers star formation, still creates tidal tails and bridges of stars, but the galaxies remain distinct, continuing on their separate paths through space. Whether galaxies merge or separate depends on their relative velocities and the geometry of their encounter. A head-on collision at low relative velocity will almost certainly result in merger. A glancing blow at high velocity might result in disruption, but not merger, with the galaxies passing through each other and continuing on, scarred but separate. The Cartwheel Galaxy, located about 500 million light-years away, is the result of a high-speed collision between a large disk galaxy and a smaller galaxy. The smaller galaxy punched through the disk of the larger galaxy like a bullet through a target, creating a ring of star formation that expanded outward from the impact point, like a ripple on a pond. The ring is now about 150,000 light-years in diameter, glowing with the light of newly formed stars. The collision compressed the gas in the disk, triggering a wave of star formation that propagated outward, creating the distinctive ring structure. The cartwheel is a rare and beautiful example of a particular type of collision, a cosmic accident frozen in time, visible to us because the light from the collision has been traveling for 500 million years to reach our telescopes. Hoag's object is another ring galaxy, though its origin is more mysterious. Located about 600 million light-years away, it consists of a nearly perfect ring of bright blue stars, surrounding a yellow core with a gap of nearly empty space between them. The ring is about 100,000 light-years in diameter, and the symmetry is so perfect that it seems almost artificial. While some ring galaxies are clearly the result of collisions, Hoag's object shows no obvious signs of a recent collision. No disturbed companion galaxy, no tidal tails. Its formation remains a puzzle, though the most likely explanation is still a collision, perhaps with a smaller galaxy that has since dispersed or escaped. Galaxy clusters, the largest gravitationally bound structures in the universe, are environments where galaxy collisions are common. Clusters can contain hundreds or thousands of galaxies, all orbiting within a shared gravitational potential well. Within these clusters, galaxies move at high speeds, hundreds or thousands of kilometers per second, and collisions are frequent. The galaxies in the centers of clusters have often merged multiple times, growing into giant elliptical galaxies that dominate the cluster. These central galaxies are among the largest and most massive galaxies in the universe, having grown fat on a diet of smaller galaxies consumed over billions of years. The Bullet Cluster, located about 3.7 billion light-years away, is actually two galaxy clusters that have collided and passed through each other. The collision was so violent that it separated the galaxies from the hot gas that filled the space between them. The galaxies, being mostly empty space, passed through each other with few direct collisions, but the gas clouds collided and were slowed by friction, creating a shock wave that heated the gas to millions of degrees, making it glow in X-rays. Observations of the Bullet Cluster provided some of the strongest evidence for dark matter, because the gravitational lensing effect, the bending of light by gravity, showed that most of the mass in the system was not where the visible galaxies or the hot gas were located, but in invisible halos surrounding the galaxies. The dark matter passed through the collision unaffected, just like the galaxies, because it doesn't interact electromagnetically, doesn't experience friction. Galactic cannibalism is the process by which large galaxies grow by consuming smaller ones. The Milky Way is currently in the process of cannibalizing several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which is being torn apart by tidal forces as it orbits through the Milky Way's disk. Streams of stars from the Sagittarius dwarf wrap around the Milky Way, evidence of the ongoing destruction. Over the next few billion years, the Sagittarius dwarf will be completely absorbed, its stars becoming part of the Milky Way's halo, its identity erased. This is the fate of most dwarf galaxies that venture too close to larger galaxies. They are pulled apart, consumed, their stars scattered and absorbed. Stephan's Quintet, a compact group of 5 galaxies located about 290 million light-years away, provides a laboratory for studying multiple galaxy interactions simultaneously. 4 of the 5 galaxies are gravitationally bound and interacting, pulling on each other, distorting each other's structures, triggering star formation. The fifth galaxy is actually much closer to us, just happening to lie in the same line of sight, not physically associated with the group. The four interacting galaxies show clear signs of their encounters: tidal tails, bridges of stars connecting them, regions of intense star formation where gas clouds have collided. Eventually, these four galaxies will merge into a single large elliptical galaxy, but the process will take billions of years. The timescales of galaxy collisions are almost incomprehensible. From first approach to final merger can take billions of years, longer than the current age of the solar system, longer than life has existed on Earth. Any civilization witnessing such a collision would see it unfold over millions of generations, would have to maintain records and observations across timescales that dwarf human history. The collision would be a constant presence in the sky, slowly changing, the two galaxies drawing closer, merging, their structures transforming. But the changes would be glacially slow, imperceptible in a human lifetime, visible only through careful measurements and long-term observations. And so tonight, as you feel sleep approaching, imagine two spiral galaxies slowly falling toward each other through the darkness. They've been approaching for hundreds of millions of years, pulled together by gravity, their fate sealed by the laws of physics. They're beautiful, these galaxies, their spiral arms traced in blue and pink, their cores glowing yellow, their halos of stars extending far into space. As they draw closer, tidal forces begin to pull at their structures, drawing out long streams of stars, distorting the elegant spiral patterns. The first close passage is spectacular. The galaxies sweep past each other, their stars interpenetrating, their gas clouds colliding and igniting in bursts of star formation. Then they separate, moving apart, but gravity pulls them back, and they fall together again and again, each passage bringing them closer, mixing their stars more thoroughly, until finally they settle into a single merged galaxy, larger than either of the originals, but no longer spiral, no longer graceful, just a vast elliptical cloud of stars, quiet and ancient. The dance is over, the merger is complete, and the universe continues, patient and indifferent, as it always has, as it always will. Let that slow transformation carry you into sleep now. Let the knowledge that even galaxies change, that even the largest structures in the universe are temporary, that everything is in motion, everything is evolving. Let that perspective settle over you. You are part of a universe in constant transformation, where nothing is permanent, where everything is connected by gravity and time. Rest now in the space between colliding galaxies, in the quiet void where the dance unfolds over billions of years. The galaxies will continue their merger whether you watch or not. You can sleep knowing that the universe is doing what it has always done, what it will always do, transforming, evolving, creating new structures from old. The collision is beautiful, patient, and the universe is not uniformly filled with galaxies. If you could step back far enough to see the large-scale structure of the cosmos, you would see that galaxies arranged in a cosmic web, filaments and sheets of matter surrounding vast empty regions called voids. These voids are the largest structures in the universe, regions hundreds of millions of light years across that contain very few galaxies, where the density of matter is far below the cosmic average. They are not completely empty. There are isolated galaxies, wisps of gas, the invisible presence of dark matter, but compared to the dense galaxy clusters and filaments, the voids are profoundly empty, silent cathedrals of space, where light travels for eons, without encountering much of anything. Tonight we drift into these empty places, these cosmic deserts, and discover that emptiness has its own beauty, its own significance, its own role in the structure of everything. The cosmic web is the largest known structure in the universe, a network of galaxy filaments separated by voids. The filaments are like the edges of soap bubbles, thin sheets and strings of galaxies surrounding empty volumes. The voids are the interiors of the bubbles, vast regions where galaxies are rare. This structure emerged from tiny density fluctuations in the early universe, regions that were slightly denser than average, and regions that were slightly less dense. Gravity amplified these differences over billions of years. The denser regions attracted more matter, growing into galaxy clusters and filaments. The less dense regions became voids, as matter drained out of them and into the surrounding filaments. The result is the cosmic web we see today, a structure that spans the observable universe, a pattern written in galaxies and empty space. The Boötes void, discovered in 1981, was one of the first large voids to be identified. It's located about 700 million light-years from Earth and measures approximately 330 million light-years in diameter. Within this enormous volume, there are only about 60 galaxies, compared to the thousands that would be expected in a typical region of that size. The void is so empty that if the Milky Way were located in its center, we would not have discovered other galaxies until the 1960s. They would have been too far away for earlier telescopes to detect. The Boötes void is sometimes called the Great Nothing, a name that captures both its emptiness and its mystery. What would it be like to live in a galaxy in the center of such a void? To look out and see almost nothing, to have no nearby neighbors, to be profoundly isolated in the vastness of space. Voids are not completely devoid of matter. They contain isolated galaxies, often small and dim, that for some reason did not migrate into the surrounding filaments. These void galaxies tend to be younger and bluer than galaxies in denser regions, still forming stars at a steady rate. They're also more likely to be spiral galaxies rather than ellipticals, because they haven't experienced the mergers and interactions that are common in denser environments. A void galaxy lives a quiet life, undisturbed by neighbors, evolving in isolation, forming stars at its own pace, without interference. There's something peaceful about that. The idea of a galaxy alone in the darkness, doing what galaxies do, untroubled by the chaos of clusters and collisions. The properties of void galaxies reveal important information about galaxy evolution. In dense environments, galaxies frequently interact, merge, and have their gas stripped away by the hot intergalactic medium. But void galaxies are spared these disruptions. They retain their gas longer, continue forming stars for extended periods, and maintain their spiral structures. Comparing void galaxies to galaxies in clusters helps astronomers understand which aspects of galaxy evolution are driven by internal processes and which are driven by environmental effects. The void galaxies are control groups in a cosmic experiment, showing us what galaxies look like when left alone. The local void is a relatively small void in our cosmic neighborhood, only about 150 million light-years across. The Milky Way sits on the edge of this void, in a filament that separates the local void from other voids. Looking in one direction, we see the rich structure of the Virgo supercluster, with its thousands of galaxies. Looking in the other direction, we see the local void, a region of relative emptiness. We are, in a sense, living on the shore of a cosmic ocean of emptiness, looking out across a vast expanse where galaxies are rare, and the darkness is deeper. The KBC void, named after its discoverers Keenan, Barger, and Cowie, is a controversial proposed void that would be enormous if it exists, about 2 billion light-years in diameter, with the Milky Way located near its center. The evidence for this void is debated, but if it's real, it would have significant implications for cosmology. Living in a large void would mean that the local density of matter around us is lower than the cosmic average, which could affect measurements of the universe's expansion rate and other cosmological parameters. It's a reminder that our location in the universe might not be typical, that we might be observing from a special position, and that we need to account for this when interpreting our observations. Voids expand over time as the universe expands. The galaxies in the filaments surrounding a void are gravitationally bound to each other and don't participate in the expansion. They're held together by gravity. But the voids themselves expand with the universe, growing larger as space itself expands. This means that voids are getting emptier, that the cosmic web is becoming more pronounced, that the contrast between dense regions and empty regions is increasing. The universe is becoming more structured, more organized, with matter concentrating in filaments and clusters, while voids grow larger and emptier. The formation of voids is intimately connected to dark matter. The cosmic web structure we see in the distribution of galaxies is actually tracing the distribution of dark matter, which outweighs ordinary matter by a factor of about 5 to 1. Dark matter formed the gravitational scaffolding upon which galaxies assembled. Where dark matter was dense, galaxies formed. Where dark matter was sparse, voids emerged. We can't see dark matter directly, but we can see its effects in the large-scale structure of the universe, in the pattern of filaments and voids that spans the cosmos. The Eridanus supervoid is an exceptionally large and empty region of space, about 1 billion light-years across, located in the direction of the constellation Eridanus. This void is notable because it appears to be associated with a cold spot in the cosmic microwave background radiation, the afterglow of the Big Bang. The cold spot is a region where the temperature of the microwave background is slightly lower than average. And one explanation is that photons lose energy as they pass through the supervoid, a phenomenon called the integrated Sachs-Wolf effect. The connection between the void and the cold spot is still being studied, but it suggests that even empty regions of space can leave their mark on the most ancient light in the universe. The Sculptor void is another significant empty region, located in the direction of the constellation Sculptor, about 300 million light-years away. Like other voids, it contains far fewer galaxies than would be expected in a typical volume of space. The void is roughly spherical, with a diameter of about 150 million light-years, and it's surrounded by filaments of galaxies that mark its boundaries. The Sculptor void is part of the larger cosmic web structure in our local universe, one of many voids that give the cosmos its characteristic foam-like appearance on the largest scales. Traveling through a void would be a strange experience. If you were in a spacecraft moving through the center of a large void, you would see very few galaxies in any direction. The sky would be mostly dark, with only scattered distant points of light marking the filaments surrounding the void. There would be no nearby galaxies to study, no rich clusters to observe, just emptiness stretching in all directions. The isolation would be profound, the silence absolute. But you would also have an unobstructed view of the distant universe, of the cosmic microwave background, of the large-scale structure. Sometimes emptiness provides the clearest view. The study of voids has revealed that they're not perfectly spherical or smooth. They have structure, with smaller voids nested inside larger ones, with tendrils of galaxies penetrating into them with irregular boundaries. The cosmic web is fractal-like, showing structure on multiple scales. Zoom in on a filament, and you'll see it's made of smaller filaments and clusters. Zoom in on a void, and you'll see smaller voids and isolated galaxies. The pattern repeats a hierarchy of structure from the smallest scales to the largest. Voids play an important role in testing cosmological theories. The size, shape, and distribution of voids depend on the properties of dark matter, dark energy, and the initial conditions of the universe. By mapping voids and measuring their properties, astronomers can test different cosmological models, can constrain the nature of dark energy, can learn about the early universe. Voids are not just empty space, they're laboratories for cosmology, regions where the effects of cosmic expansion and dark energy are particularly clear. The Sloan Great Wall, one of the largest known structures in the universe, is actually defined by the voids it surrounds. This massive filament of galaxies stretches for about 1.4 billion light-years and contains hundreds of thousands of galaxies. But it's the voids on either side of the wall that make it so prominent. The contrast between the dense filament and the empty voids creates one of the most striking features in the large-scale structure of the universe. The wall itself is not a solid structure, but a concentration of galaxies along a filament, a cosmic highway surrounded by cosmic deserts. The future of voids is expansion. As the universe continues to expand, accelerated by dark energy, voids will grow larger. The filaments and clusters will remain gravitationally bound, but the voids between them will expand, and the universe will become increasingly empty on large scales. Eventually, in the far future, the expansion will have carried distant galaxies beyond our cosmic horizon, and the observable universe will contain only the galaxies in our local group, which will have merged into a single galaxy. The rest of the universe will have receded beyond visibility, and we will be surrounded by an ever-growing void, alone in the darkness. Voids play an important role in testing cosmological theories. The size, shape, and distribution of voids depend on the properties of dark matter, dark energy, and the initial conditions of the universe. By mapping voids and measuring their properties, astronomers can test different cosmological models, can constrain the nature of dark energy, can learn about the early universe. Voids are not just empty space, they're laboratories for cosmology, regions where the effects of cosmic expansion and dark energy are particularly clear. The Sloan Great Wall, one of the largest known structures in the universe, is actually defined by the voids it surrounds. This massive filament of galaxies stretches for about 1.4 billion light-years and contains hundreds of thousands of galaxies. But it's the voids on either side of the wall that make it so prominent. The contrast between the dense filament and the empty voids creates one of the most striking features in the large-scale structure of the universe. The wall itself is not a solid structure, but a concentration of galaxies along a filament, a cosmic highway surrounded by cosmic deserts. The future of voids is expansion. As the universe continues to expand, accelerated by dark energy, voids will grow larger. The filaments and clusters will remain gravitationally bound, but the voids between them will expand, and the universe will become increasingly. Voids play an important role in testing cosmological theories. The size, shape, and distribution of voids depend on the properties of dark matter, dark energy, and the initial conditions of the universe. By mapping voids and measuring their properties, astronomers can test different cosmological models, can constrain the nature of dark energy, can learn about the early universe. Voids are not just empty space. Dark energy, the mysterious force driving the accelerated expansion of the universe, is particularly evident in voids. While gravity pulls matter together in filaments and clusters, dark energy pushes space apart everywhere. But its effects are most noticeable in regions where gravity is weakest, in the voids. The expansion of voids is accelerating, driven by dark energy, and measuring this acceleration helps astronomers understand the nature of dark energy itself. The voids are cosmic laboratories, where one of the universe's greatest mysteries reveals itself most clearly. And so tonight, as sleep draws closer, imagine yourself floating in the center of a great void, surrounded by emptiness in all directions. The nearest galaxy is hundreds of millions of light years away, a faint smudge of light barely visible against the darkness. There are no stars here, no planets, no matter except the occasional atom of hydrogen drifting through the void. The silence is absolute. There is no sound, no light, no disturbance, just the slow expansion of space itself, carrying the distant galaxies farther away with each passing moment. You are alone in the vastness, but there's no fear here, no anxiety. The emptiness is peaceful, restful, a reminder that the universe contains not just matter and energy, but also space, silence, absence. The voids are as much a part of the cosmos as the galaxies, as essential to the structure as the filaments and clusters. Let that emptiness settle over you now. Let the silence of the voids, the profound peace of regions where nothing happens, where nothing disturbs the darkness, let that carry you into sleep. The voids are expanding, growing larger, becoming emptier. And there's something deeply calming about that. The knowledge that the universe contains vast regions of nothing. That emptiness is not a failure, but a feature, a necessary part of the cosmic architecture. Rest now in the great void, in the silent space between galaxies. There is nothing here to worry about, nothing to disturb you, just the gentle expansion of space and the distant fading light of galaxies receding into the darkness. Sleep now. The void will hold you. The emptiness will keep you safe. At the center of nearly every large galaxy, hidden behind veils of stars and dust, lies a supermassive black hole, an object so dense, so gravitationally powerful, that not even light can escape once it crosses the event horizon. These black holes contain millions or billions of times the mass of our Sun, compressed into a region smaller than our solar system. They are invisible, detectable only by their effects on surrounding matter, by the stars that orbit them at tremendous speeds, by the jets of radiation they produce when actively feeding. They are the dark hearts of galaxies, the gravitational anchors around which hundreds of billions of stars orbit, and they hold secrets about galaxy formation, about the nature of space-time, about the ultimate fate of matter. Tonight we descend toward these cosmic abysses, these points of no return, and discover that even in the darkest places in the universe, there is structure, there is beauty, there is a kind of terrible peace. Supermassive black holes are fundamentally different from stellar mass black holes, which form when massive stars collapse at the end of their lives. Stellar black holes contain a few to a few dozen solar masses. Supermassive black holes contain millions to billions of solar masses. How they formed is still not completely understood. They may have grown from smaller black holes that merged and accreted matter over billions of years. They may have formed directly from the collapse of massive gas clouds in the early universe. They may have formed from the collapse of the first generation of stars, which were far more massive than stars today. Whatever their origin, supermassive black holes were already in place when galaxies were young, already massive, already influencing the evolution of their host galaxies. The black hole at the center of the Milky Way, Sagittarius A, pronounced Sagittarius A star, contains approximately 4.1 million solar masses. It sits 26,000 light-years from Earth, hidden behind dense clouds of dust that block visible light but allow radio waves and X-rays to pass through. For years, astronomers tracked the orbits of stars near Sagittarius A, watching them whip around the invisible mass at speeds reaching a significant fraction of the speed of light. One star, designated S2, completes an orbit in just 16 years, approaching to within 17 light-hours of the black hole at its closest point. The precision of these orbital measurements allowed astronomers to calculate the mass of Sagittarius A with extraordinary accuracy, and to confirm that it must be a black hole. No other object could contain that much mass in such a small volume. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, not of Sagittarius A, but of the much larger black hole at the center of the galaxy M87. This black hole contains about 6.5 billion solar masses, over 1,000 times more massive than Sagittarius A. The image shows a dark, circular region, the black hole's shadow, surrounded by a bright ring of glowing gas. The gas is orbiting the black hole at nearly the speed of light, heated to billions of degrees by friction and magnetic fields, emitting radiation across the electromagnetic spectrum. The shadow is larger than our entire solar system, a region of space-time so warped that light cannot escape, a boundary between the observable universe and a realm forever hidden from view. The event horizon is the point of no return, the boundary surrounding a black hole beyond which escape is impossible. Once anything, matter, light, information, crosses the event horizon, it falls inexorably toward the singularity at the center, crushed to infinite density according to general relativity. For a supermassive black hole, the event horizon can be billions of miles across, far larger than the orbit of Neptune. Paradoxically, the tidal forces at the event horizon of a supermassive black hole are relatively gentle. An astronaut falling into a stellar mass black hole would be torn apart by tidal forces long before reaching the event horizon, stretched into a thin stream in a process gruesomely called spaghettification. But an astronaut falling into a supermassive black hole might cross the event horizon without even noticing, at least initially. The tidal forces increase as you approach the singularity, but at the horizon itself, they can be surprisingly mild. Time behaves strangely near a black hole. According to general relativity, time slows down in strong gravitational fields, an effect called gravitational time dilation. An observer far from a black hole watching something fall towards the event horizon would see it slow down, approaching the horizon asymptotically, never quite crossing, frozen at the boundary for eternity. But from the perspective of the falling object, time passes normally, and it crosses the event horizon in finite time, continues falling toward the singularity. The two perspectives are both correct. Both describe the same event, but they're irreconcilable, a consequence of the strange geometry of space-time near a black hole. Supermassive black holes are not always quiet. When they're actively accreting matter, pulling in gas and dust from their surroundings, they become some of the brightest objects in the universe. The infalling matter forms an accretion disk, a swirling disk of gas orbiting the black hole, heated by friction to millions of degrees, glowing brilliantly in X-rays and other wavelengths. The accretion disk can outshine the entire galaxy, making the galactic nucleus visible across billions of light-years. These active galactic nuclei, or AGN, were more common in the early universe, when galaxies were younger and gas was more abundant. Today, most supermassive black holes, including Sagittarius A, are relatively quiet, accreting matter only slowly. Their accretion disks dim or absent. Quasars are the most luminous type of active galactic nucleus, powered by supermassive black holes accreting matter at tremendous rates. The brightest quasars can be 1,000 times more luminous than the entire Milky Way. All that energy coming from a region smaller than our solar system. Quasars were most common when the universe was younger, between 1 and 3 billion years after the Big Bang. They represent a phase in galaxy evolution when supermassive black holes were growing rapidly, feeding on abundant gas, shining brilliantly. As galaxies matured and gas was consumed or expelled, quasar activity declined. The quasars we see today are distant, their light having traveled for billions of years to reach us. We're seeing them as they were in the early universe, witnessing a phase of galactic evolution that has largely ended in the local universe. Some active galactic nuclei produce jets, narrow beams of matter and energy that shoot out from the poles of the accretion disk at nearly the speed of light. These jets can extend for millions of light years, far beyond the galaxy itself, creating enormous lobes of radio emission where the jet material collides with intergalactic gas. The mechanism that produces these jets is not fully understood, but it involves the black hole's rotation and the magnetic fields threading through the accretion disk. The jets are incredibly powerful, carrying away energy and momentum, affecting the evolution of the host galaxy and even the surrounding galaxy cluster. They're among the most energetic phenomena in the universe, cosmic particle accelerators, operating on scales that dwarf anything we can create on Earth. The relationship between supermassive black holes and their host galaxies is intimate and surprising. The mass of a galaxy's central black hole is correlated with properties of the galaxy itself: the mass of the central bulge, the velocity dispersion of stars. Galaxies with more massive bulges have more massive black holes, following a tight relationship. This suggests that black holes and galaxies grow together, that their evolution is linked. The black hole, despite containing only a tiny fraction of the galaxy's total mass, somehow influences the galaxy's development. One mechanism is feedback. When the black hole is actively accreting and producing jets, it can heat or expel gas from the galaxy, suppressing star formation, regulating the galaxy's growth. The black hole acts as a thermostat, preventing the galaxy from growing too large, maintaining a balance between star formation and gas consumption. Binary supermassive black holes form when two galaxies merge. Each galaxy brings its own central black hole, and after the merger, the two black holes orbit each other at the center of the combined galaxy. Over time, they spiral closer together, losing energy through gravitational interactions with nearby stars and through the emission of gravitational waves. Eventually, they merge, creating a single more massive black hole and releasing an enormous burst of gravitational wave energy. These mergers are among the most powerful events in the universe, and future space-based gravitational wave detectors will be able to observe them, listening to the space-time ripples produced when billion solar mass black holes collide. Supermassive black holes may have intermediate mass cousins, black holes containing hundreds to thousands of solar masses, bridging the gap between stellar mass and supermassive black holes. These intermediate mass black holes are harder to detect because they don't have the obvious signatures of supermassive black holes at galactic centers, or the well-understood formation mechanism of stellar mass black holes. But there's growing evidence for their existence in dense star clusters and in the centers of some dwarf galaxies. They may represent an intermediate stage in black hole growth, seeds that could grow into supermassive black holes given enough time and matter to accrete. The singularity at the center of a black hole is where general relativity breaks down, where the equations produce infinities, where our understanding of physics fails. According to classical general relativity, all the mass of the black hole is compressed into a point of infinite density. But this is almost certainly not the true description. It's a signal that we need a theory of quantum gravity, a theory that combines general relativity with quantum mechanics to understand what really happens at the center of a black hole. The singularity is hidden behind the event horizon, forever inaccessible to outside observers. So we can't directly test our theories, but the existence of singularities suggests that our current physics is incomplete, that there are realms of nature we don't yet understand. And so tonight, as sleep finally claims you, imagine yourself at a safe distance from a supermassive black hole, watching the accretion disk spiral inward, glowing with the light of matter being torn apart and consumed. The disk is beautiful, a swirl of light and color, blues and whites where the gas is hottest, reds and oranges farther out. At the center is darkness, absolute and perfect, the event horizon, a sphere of nothingness surrounded by brilliance. Matter falls toward it in a steady stream, crossing the horizon and disappearing forever, adding its mass to the black hole, feeding the dark heart of the galaxy. The black hole doesn't care what falls in. Stars, gas, planets, light. It consumes everything equally, impartially, adding to its mass, deepening its gravitational well. There's something peaceful about that inevitability, that absolute certainty. The black hole is patient, eternal, waiting at the center of the galaxy, pulling everything toward it with gentle, inexorable gravity. Let that dark gravity pull you now, not toward destruction but toward rest, toward the deep, dreamless sleep that waits beyond the event horizon of consciousness. The black hole is there, at the center, holding the galaxy together, providing the anchor around which everything orbits. And you, safe in your bed, can orbit too, can circle the dark center, can surrender to the pull of sleep. The black hole will still be there when you wake, patient and eternal, the dark heart beating at the center of everything. Rest now, let go, fall into the darkness. It's safe there, it's quiet, it's where everything eventually goes. Galaxies are not static collections of ancient stars. They are living, breathing systems, constantly creating new stars from vast clouds of gas and dust, called nebulae. These stellar nurseries are among the most beautiful objects in the universe. Glowing clouds of hydrogen and helium, illuminated by the ultraviolet light of newborn stars, sculpted into fantastic shapes by stellar winds and radiation pressure. Within these nebulae, gravity is pulling matter together, creating dense cores that will collapse to form new stars, new planetary systems, new possibilities for worlds, and perhaps for life. Tonight, we drift through these cosmic nurseries, these places where creation is ongoing, where the raw material of the universe is being transformed into stars and planets, where the future is being born from clouds of ancient gas. The Eagle Nebula, located about 7,000 light-years away in the constellation Serpens, is one of the most iconic star-forming regions, made famous by the Hubble Space Telescope's Pillars of Creation image. These pillars are columns of dense gas and dust, each several light-years tall, being sculpted by the intense ultraviolet radiation from nearby young stars. The radiation is slowly eroding the pillars, boiling away the outer layers of gas, but the densest regions resist erosion and cast shadows, creating the pillar structures. Inside these pillars, hidden from view, new stars are forming, cocooned in dust, slowly accreting mass from the surrounding cloud. Eventually, these stars will emerge, will blow away the remaining gas with their stellar winds, will reveal themselves to the galaxy. The pillars are temporary, existing only for a few million years before being completely eroded, but they're beautiful. Monuments to the ongoing process of star formation. Star formation begins when a region of a molecular cloud becomes dense enough that its own gravity overcomes the internal pressure of the gas. This can be triggered by various events: the shock wave from a nearby supernova, the collision of two gas clouds, the compression caused by a galaxy's spiral arms. Once collapse begins, the cloud fragments into smaller clumps, each of which can form a star or a small cluster of stars. The collapsing gas heats up as gravitational potential energy is converted to thermal energy. When the core becomes hot and dense enough, nuclear fusion ignites and a star is born. The process takes millions of years for stars like the Sun, less time for more massive stars, longer for smaller stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is the nearest large star-forming region to Earth, only about 1,350 light-years away. It's a vast cloud of gas and dust, about 24 light-years across, illuminated by a cluster of young, hot stars at its center, called the trapezium. These stars, only a few million years old, are blasting the surrounding gas with ultraviolet radiation, causing it to glow in the characteristic red of ionized hydrogen. The nebula is a stellar nursery in full operation, with hundreds of young stars visible and many more still forming, hidden within dense cocoons of dust. Observations of the Orion Nebula have revealed protoplanetary disks around many of the young stars. Flattened disks of gas and dust orbiting the stars, the raw material from which planets will form. We are witnessing not just star formation, but the formation of planetary systems, seeing the process that created our own solar system playing out in real time. The Carina Nebula, located about 7,500 light-years away, is one of the largest and brightest nebulae in our galaxy, spanning over 300 light-years. It contains some of the most massive and luminous stars known, including Eta Carinae, a star system so massive and unstable that it could explode as a supernova at any time. The nebula is a chaotic region of intense star formation, with towering pillars of gas, cavities carved by stellar winds, and brilliant clusters of newborn stars. The Hubble Space Telescope has captured stunning images of the Carina Nebula, revealing intricate structures, jets of material shooting from young stars, and the beautiful interplay of light and shadow as radiation sculpts the gas into fantastic shapes. Protostars, the earliest stage of star formation, are deeply embedded in their natal clouds, invisible at optical wavelengths, but detectable in infrared and radio. These objects are still accreting matter from the surrounding cloud, growing in mass, not yet hot enough at their cores for sustained nuclear fusion. They're surrounded by accretion disks, and they often produce jets, narrow beams of material shooting out along the rotation axis at speeds of hundreds of kilometers per second. These jets are one of the mysteries of star formation, their exact mechanism still not fully understood, but they appear to be a natural consequence of the accretion process, a way for the system to shed angular momentum and allow matter to fall onto the growing protostar. Herbig-Haro objects are the visible manifestation of these protostellar jets, glowing knots and filaments where the jet material collides with the surrounding gas. They're named after George Herbig and Guillermo Haro, who first studied them in the 1950s. These objects are transient, lasting only a few thousand years, but they're beautiful, glowing in the light of shocked gas, revealing the violent processes occurring around young stars. Studying Herbig-Haro objects helps astronomers understand how stars form, how they interact with their environment, how planetary systems emerge from the chaos of collapsing gas clouds. The Tarantula Nebula, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, is the most active star-forming region in the local group of galaxies. It's about 1,000 light-years across and contains hundreds of thousands of young stars, including some of the most massive stars ever discovered. The nebula is so bright that if it were located at the distance of the Orion Nebula, it would cast shadows on Earth. The Tarantula is a glimpse of what star formation looked like in the early universe, when galaxies were younger and gas was more abundant, when star formation rates were much higher than they are today. It's a reminder that the universe was once a more active, more violent place, full of intense star formation and energetic events. Massive stars, those with more than 8 times the mass of the Sun, have profound effects on their surroundings. Their intense ultraviolet radiation ionizes the surrounding gas, creating HII regions, vast bubbles of glowing hydrogen. Their stellar winds, streams of particles flowing from their surfaces at thousands of kilometers per second, sweep up the surrounding gas, creating shells and cavities. And when they die, they explode as supernovae, releasing enormous amounts of energy, enriching the interstellar medium with heavy elements, triggering new waves of star formation. Massive stars are the sculptors of galaxies, shaping the structure of the interstellar medium, regulating star formation, creating the conditions for future generations of stars and planets. The interstellar medium, the gas and dust between the stars, is not uniform. It exists in different phases: cold molecular clouds where stars form, warm neutral hydrogen, hot ionized gas, heated by supernovae and stellar winds. These phases are constantly interacting, transforming into each other, creating a dynamic, evolving medium. The molecular clouds are the densest and coldest phase, with temperatures just a few degrees above absolute zero and densities high enough for molecules to form. These clouds are the raw material for star formation, the reservoirs from which galaxies draw to create new stars. Dust plays a crucial role in star formation. The tiny grains of dust, made of silicates and carbon compounds, provide surfaces where molecules can form, shielding the interior of clouds from ultraviolet radiation, allowing the gas to cool and collapse. Dust also absorbs starlight and re-emits it in the infrared, making dusty regions visible to infrared telescopes, even when they're opaque at optical wavelengths. The dust grains themselves are created in the atmospheres of dying stars and in supernova explosions, then dispersed into the interstellar medium, incorporated into new molecular clouds, and eventually into new stars and planets. The dust in your body, the carbon and silicon and iron, was created in stars, dispersed as dust, incorporated into the molecular cloud that formed the Sun, and eventually assembled into planets and life. Planetary systems form from the leftover material in the accretion disk around a young star. The disk is initially smooth, but over time, dust grains collide and stick together, growing into larger particles, then pebbles, then boulders, then planetesimals, objects kilometers in size. These planetesimals collide and merge, growing into protoplanets and eventually into full-sized planets. The process takes millions of years and is chaotic, with countless collisions, near misses, and gravitational interactions. The final configuration of a planetary system depends on many factors: the mass of the star, the composition and mass of the disk, the presence of giant planets that can migrate and disrupt the orbits of smaller bodies. Every planetary system is unique, shaped by its particular history of formation and evolution. The discovery of exoplanets, planets orbiting stars other than the Sun, has revealed that planetary systems are common, that most stars have planets, that the galaxy is full of worlds. Some of these worlds are similar to Earth, rocky planets in the habitable zone where liquid water could exist on the surface. Others are utterly alien, hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths with no analogue in our solar system, planets orbiting binary stars, or even free-floating through space without a star at all. The diversity is staggering, and it suggests that the processes of planet formation are robust, that given a star and a disk of material, nature will find ways to create planets. And so tonight, as you surrender to sleep, imagine yourself floating through the Eagle Nebula, through the pillars of creation. The gas glows softly around you, red and pink from ionized hydrogen, blue from reflected starlight. You can see young stars embedded in the pillars, their light filtering through the dust, creating a diffuse glow. Deeper inside, hidden from view, protostars are forming, pulling in matter from the surrounding cloud, growing, preparing to ignite fusion and join the community of stars. This is where creation happens, where the universe makes new stars, new worlds, new possibilities. The process is slow, patient, operating on timescales of millions of years, but it's continuous, ongoing, happening right now in nebulae throughout the galaxy. Let that knowledge settle over you, that creation is not a past event, but an ongoing process, that the universe is still making stars, still making worlds, still exploring possibilities. You are made of material that went through this process billions of years ago, forged in stars, dispersed in nebulae, incorporated into a new star system, assembled into a planet, and eventually into you. You are stardust, literally a temporary arrangement of atoms that were created in stellar furnaces and will eventually return to the cosmos. Let that cosmic perspective carry you into sleep now. Let the glowing nebulae, the forming stars, the emerging planetary systems, let all of that remind you that you're part of an ongoing story, a universe that creates and destroys, that transforms matter endlessly, that makes stars and planets, and perhaps, on some of those planets, life and consciousness. Rest now in the stellar nursery, in the glowing clouds where creation is happening. The nebulae will still be forming stars when you wake. The universe will still be creating, and you, for this brief moment, are part of that creation, a conscious witness to the cosmic process. Sleep now, dream of nebulae and newborn stars, of planets forming in dusty disks, of the endless creativity of the universe. Looking at distant galaxies is looking backward through time. Light travels at a finite speed, 186,000 miles per second, fast by human standards but slow on cosmic scales. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star takes over 4 years. Light from distant galaxies takes millions, billions of years. When we observe a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago, when the universe was young, when the first generations of stars were being born, when galaxies were just beginning to assemble from the primordial gas. These ancient galaxies are ghosts, images from a past so distant that the galaxies themselves may no longer exist in the forms we see. Tonight, we look backward through cosmic time, witnessing the birth and evolution of galaxies, seeing the universe transform from a simple, smooth state into the rich, structured cosmos we inhabit today. The most distant galaxies we can observe are seen as they were when the universe was only a few 100 million years old, less than 5% of its current age. These galaxies are small, irregular, nothing like the grand spirals and ellipticals we see in the nearby universe. They're forming stars at prodigious rates, burning through their gas supplies quickly, building up stellar mass. They're also metal poor. The heavy elements that make up planets and life are rare because there haven't been many generations of stars to create them. These early galaxies are cosmic pioneers, the first structures to emerge from the darkness of the cosmic dark ages, the period after the Big Bang when the universe was filled with neutral hydrogen, opaque to visible light. The Hubble ultra-deep field, an image created by pointing the Hubble Space Telescope at a tiny patch of apparently empty sky for nearly 1 million seconds, revealed thousands of galaxies, many of them extremely distant and faint. This image, covering an area of sky smaller than a grain of sand held at arm's length, contains galaxies from nearly every epoch of cosmic history. The nearest galaxies appear large and detailed, showing spiral arms and structure. The most distant appear as tiny red smudges, their light stretched to longer wavelengths by the expansion of the universe, seen as they were over 13 billion years ago. The ultra-deep field is a time machine, a single image that captures the evolution of galaxies across cosmic history. The Hubble Extreme Deep Field pushed even deeper, combining data from multiple observations to reveal galaxies at even greater distances. This image contains approximately 5,500 galaxies, with some dating back to just 450 million years after the Big Bang. The faintest galaxies in the image are 10 billion times fainter than what the human eye can see. Each of these tiny points of light represents an entire galaxy containing billions of stars, seen across vast gulfs of space and time. The image is a testament to human curiosity, to our desire to see farther, to understand our cosmic origins, to witness the universe as it was in its infancy. The redshift of a galaxy tells us how much the universe has expanded since the light left that galaxy. Light is stretched as it travels through expanding space, shifting toward longer, redder wavelengths. The amount of redshift indicates the distance and the look-back time, how far back in time we're seeing the galaxy. Galaxies with redshifts of 1 or 2 are seen as they were several billion years ago. Galaxies with redshifts of 6 or 7 are seen as they were when the universe was less than 1 billion years old. The most distant galaxies detected have redshifts greater than 10, seen as they were just a few 100 million years after the Big Bang. These redshifts are not caused by the galaxies moving through space, but by the expansion of space itself, carrying the galaxies apart and stretching the light traveling between them. GN-Z11, one of the most distant galaxies ever observed, has a redshift of 11.1, meaning we see it as it was about 400 million years after the Big Bang. Despite its extreme distance, it's surprisingly bright and massive, containing about 1 billion solar masses of stars. This suggests that galaxy formation began early, that the first galaxies assembled quickly from the primordial gas. GN-Z11 is forming stars at a rate about 20 times higher than the Milky Way does today, burning bright in the young universe. By now, 13.4 billion years later, this galaxy has evolved, has merged with other galaxies, has become part of a larger structure. We'll never see what it looks like today. The light showing its current state won't reach us for billions of years. The James Webb Space Telescope, launched in 2201, is designed specifically to observe these distant, early galaxies. Its large mirror and infrared sensitivity allow it to detect the faint, red-shifted light from galaxies formed in the first few 100 million years after the Big Bang. Early observations from Webb have revealed galaxies that are more massive and more structured than expected at such early times, challenging our understanding of how quickly galaxies can form and evolve. The universe appears to have been more efficient at forming galaxies than our models predicted, creating substantial structures earlier than we thought possible. MACS 0647 JD is another extremely distant galaxy discovered behind a massive galaxy cluster that acts as a gravitational lens, magnifying the distant galaxy's light. It's seen as it was when the universe was only 420 million years old, making it one of the earliest galaxies ever observed. The galaxy is tiny, only about 600 light-years across, far smaller than the Milky Way, but it's actively forming stars, building up mass that will eventually contribute to larger galaxies through mergers. These small early galaxies are the building blocks of the universe, the seeds from which all later structure grew. Lyman alpha emitters are a class of distant galaxies identified by their strong emission of Lyman alpha radiation, a specific wavelength of ultraviolet light produced by hydrogen. In nearby galaxies, this radiation is absorbed by intervening gas and dust, but in very distant galaxies, the expansion of the universe has redshifted the Lyman alpha light into the visible spectrum, making these galaxies easier to detect. Lyman alpha emitters are typically young, actively forming stars, and they provide a way to study galaxy formation in the early universe. Surveys have identified thousands of these galaxies, creating a census of star formation across cosmic time. The cosmic star formation rate has changed dramatically over the history of the universe. Star formation peaked when the universe was about 3 billion years old, an era sometimes called cosmic noon, when galaxies were forming stars at rates 10 times higher than today. Since then, star formation has been declining as galaxies exhaust their gas supplies and as the expansion of the universe makes it harder for gas to fall into galaxies. The universe is slowly fading, transitioning from a period of vigorous star formation to a quieter era dominated by old red stars. Eventually, in the far future, star formation will cease entirely as all available gas is consumed or dispersed, and the universe will grow dark. The morphology of galaxies has evolved over cosmic time. In the nearby universe, about 2/3 of large galaxies are spirals or irregulars, with the rest being ellipticals. But in the distant universe, at high redshifts, the proportion is reversed. Most galaxies are irregular or peculiar, with fewer well-defined spirals. This suggests that spiral structure develops over time, that galaxies in the early universe were more chaotic, more actively merging and interacting. The beautiful spiral galaxies we see today are mature structures, the result of billions of years of evolution and settling. Quasars in the early universe provide information about the growth of supermassive black holes. Some quasars are observed at redshifts greater than 6, meaning they existed when the universe was less than 1 billion years old, yet they're powered by black holes containing billions of solar masses. How these black holes grew so massive so quickly is a puzzle. They may have formed from the direct collapse of massive gas clouds, or from the rapid merger of smaller black holes, or through super-Eddington accretion, where matter falls onto the black hole faster than standard models predict. The existence of these early quasars tells us that black hole growth and galaxy formation are intimately connected, that the processes shaping galaxies began very early in cosmic history. Gravitational lensing allows us to see even more distant galaxies by using the gravity of foreground galaxy clusters to magnify and brighten background galaxies. The cluster's gravity bends the light from distant galaxies, acting like a cosmic telescope, magnifying them by factors of 10 or more. This allows astronomers to study galaxies that would otherwise be too faint to detect, to see details in early galaxies that would be impossible to resolve directly. Some of the most distant galaxies known were discovered this way, their light magnified by the fortuitous alignment of a massive cluster between us and them. The reionization epoch, occurring between about 150 million and 1 billion years after the Big Bang, was when the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen filling the universe. Before reionization, the universe was opaque to visible light, filled with neutral hydrogen that absorbed photons. After reionization, the universe became transparent, allowing light to travel freely across cosmic distances. The first galaxies were the agents of reionization, their hot, massive stars producing the ultraviolet radiation that transformed the universe from opaque to transparent. Studying the most distant galaxies helps us understand this crucial transition, this moment when the universe emerged from darkness into light. The chemical evolution of galaxies is written in their spectra. Early galaxies are metal-poor, containing mostly hydrogen and helium, the elements created in the Big Bang. As stars form, live, and die, they create heavier elements, carbon, oxygen, iron, and disperse them into the interstellar medium through stellar winds and supernova explosions. Each generation of stars is slightly more metal-rich than the last, building up the abundance of heavy elements over time. By measuring the metallicity of distant galaxies, astronomers can trace this chemical enrichment across cosmic history, can see how the universe transformed from a simple mixture of hydrogen and helium into the chemically complex cosmos we inhabit today. The cosmic microwave background, the afterglow of the Big Bang, provides a backdrop against which we can study the earliest galaxies. This radiation, emitted when the universe was only 380,000 years old, fills all of space, appearing as a faint glow at microwave wavelengths. The first galaxies formed in regions where the density of matter was slightly higher than average, regions that appear as tiny fluctuations in the temperature of the microwave background. These fluctuations, only a few parts per million, were the seeds of all later structure, the tiny variations that gravity amplified over billions of years to create galaxies, clusters, and the cosmic web. The universe is not static, not settled, not finished. Everything is moving, flowing, evolving toward futures we can only glimpse through mathematics and observation. Our local group of galaxies is falling towards something massive and distant, an enormous concentration of mass called the Great Attractor. Beyond that lies an even larger structure, the Shapley supercluster, pulling on vast regions of space. And beyond all the local motions, the universe itself is expanding, accelerating, driven by dark energy, carrying distant galaxies away from us at ever-increasing speeds. The future of the cosmic web is written in these motions, in the interplay of gravity and expansion, in the slow transformation of structure over timescales that dwarf the current age of the universe. Tonight, we look forward as well as backward, contemplating the ultimate fate of galaxies, the distant future when the cosmos will be unrecognizably different from what we see today. The Great Attractor is a gravitational anomaly, a region of space toward which the Milky Way and hundreds of thousands of other galaxies are flowing. It's located about 150 to 250 million light-years away, in the direction of the constellations Triangulum Australe and Norma, hidden behind the plane of the Milky Way where dust obscures our view. The Great Attractor isn't a single object, but a region of unusually high galaxy density, part of the larger Laniakea supercluster, which contains about 100,000 galaxies, including our own. The name Laniakea means immeasurable heaven in Hawaiian, a fitting name for a structure so vast that light takes 520 million years to cross it. Our motion through space is complex, a combination of multiple flows. The Sun orbits the center of the Milky Way at about 515,000 miles per hour. The Milky Way is falling toward Andromeda at about 250,000 miles per hour, and the entire local group is moving toward the Great Attractor at about 1.3 million miles per hour. These motions are superimposed on the general expansion of the universe, creating a complex pattern of movement where some galaxies are approaching us while most are receding. We are not at rest in the universe. We're passengers on multiple cosmic currents, flowing toward massive structures, orbiting within our galaxy, participating in the great dance of matter through space and time. The zone of avoidance is the region of sky obscured by the plane of the Milky Way, where dust blocks our view of distant galaxies. The Great Attractor lies within this zone, making it difficult to study directly at optical wavelengths. Astronomers have had to use radio, infrared, and X-ray observations to peer through the dust and map the structure hidden behind our galaxy. These observations have revealed massive galaxy clusters in the zone of avoidance, including the Norma cluster and the Vela supercluster, structures that contribute to the gravitational pull we're experiencing. The zone of avoidance is a reminder that our location within the Milky Way limits our view, that there are regions of the universe we can only glimpse indirectly. The Shapley supercluster, located about 650 million light-years away, is one of the most massive structures in the nearby universe, containing over 8,000 galaxies, with a total mass of about 10,000 trillion suns. It's so massive that it affects the motion of galaxies over 1 billion light-years away, including our own. The Shapley supercluster is pulling on the Great Attractor, which in turn is pulling on us, creating a flow of galaxies across hundreds of millions of light-years. This structure demonstrates that even on the largest scales, gravity still matters, still shapes the motion of matter, still creates patterns in the distribution of galaxies. The discovery of the Laniakea supercluster in 2014 redefined our cosmic address. Before this discovery, we thought the Milky Way was part of the Virgo supercluster, a collection of galaxy groups and clusters spanning about 110 million light-years. But detailed mapping of galaxy velocities revealed that the Virgo supercluster is just one component of the much larger Laniakea supercluster, and that galaxies across this vast region are all flowing toward a common gravitational basin. Laniakea is our true cosmic home, the largest structure to which we gravitationally belong, the region of space whose fate is tied to our own. The cosmic web, the network of filaments, sheets, and voids that makes up the large-scale structure of the universe, is not static. It's evolving, with matter continuing to flow along filaments towards the densest regions, with voids expanding, with clusters growing more massive as they accrete galaxies from their surroundings. But this evolution is slowing. The expansion of the universe, driven by dark energy, is working against gravity, making it harder for structures to grow, eventually halting the assembly of new large-scale structures. The cosmic web we see today represents a peak in structure formation, the universe will never be more richly structured than it is now. Dark energy, the mysterious force causing the universe's expansion to accelerate, makes up about 68% of the total energy content of the universe. Its nature is unknown. It might be a property of space itself, a cosmological constant as Einstein proposed, or it might be a dynamic field that changes over time. Whatever it is, dark energy is winning the battle against gravity. On scales larger than galaxy clusters, expansion dominates, carrying structures apart faster than gravity can pull them together. The cosmic web is being stretched, with filaments thinning, voids growing, and the universe becoming increasingly empty on the largest scales. The future of galaxy clusters is isolation. Clusters are gravitationally bound, so they won't participate in the cosmic expansion. The galaxies within them will continue to orbit each other, will merge over time, will eventually combine into a single giant elliptical galaxy. But the clusters themselves will become increasingly isolated as the expansion of space carries other clusters beyond the cosmic horizon, the distance beyond which light can never reach us, because space is expanding faster than light can travel through it. Eventually, each cluster will be alone in an expanding void, unable to see or interact with other clusters, isolated islands in an ever-growing ocean of empty space. The local group, the Milky Way, Andromeda, and their satellite galaxies, will merge over the next several billion years. The Milky Way and Andromeda will collide, as we've discussed, creating a single large elliptical galaxy. The smaller galaxies in the local group will either merge with this combined galaxy or be flung into intergalactic space by gravitational interactions. Eventually, perhaps 10 billion years from now, the local group will have consolidated into a single galaxy, a massive elliptical containing all the stars from all the galaxies that once orbited independently. This merged galaxy will be the entire observable universe for any civilizations that exist at that time. All other galaxies will have receded beyond the cosmic horizon, carried away by expansion. The cosmic horizon is shrinking in terms of what we can see. While the universe is expanding and the physical distance to distant galaxies is increasing, the number of galaxies we can observe is actually decreasing. Galaxies that are currently visible will eventually recede beyond the cosmic horizon as the accelerating expansion carries them away faster than their light can reach us. In about 100 billion years, all galaxies outside our local supercluster will have disappeared from view, and observers in the far future will see a much emptier universe than we do. With no evidence of the cosmic expansion, no distant galaxies to study, no way to discover the Big Bang, or the true scale of the cosmos. The ultimate fate of galaxies depends on the nature of dark energy. If dark energy remains constant, the universe will continue expanding forever, growing colder, darker, emptier. Star formation will cease as galaxies exhaust their gas supplies. Existing stars will age and die, with no new stars to replace them. Eventually, in about 100 trillion years, the last stars will burn out, and the universe will enter the degenerate era, filled with dead stellar remnants, white dwarfs, neutron stars, black holes, but no living stars. The galaxies will be dark, invisible, their matter locked in compact objects that emit no light. But even this is not the end. Over timescales almost incomprehensibly long, 10 circumflex 100 years and beyond, even the dead remnants will decay or evaporate. Protons may decay if certain theories of physics are correct, causing even white dwarfs and neutron stars to slowly disintegrate. Black holes will evaporate through Hawking radiation, a quantum process that allows them to slowly lose mass, eventually disappearing in a final burst of radiation. The timescale for this evaporation depends on the black hole's mass. Stellar mass black holes will evaporate in about 10 circumflex 67 years. Supermassive black holes in about 10 circumflex 100 years. These numbers are so large they're almost meaningless, but they represent the ultimate fate of all structure, all matter, all the galaxies and stars and planets that once existed. The black hole era will be the longest epoch in the universe's history, lasting from about 10 circumflex 40 years to 10 circumflex 100 years after the Big Bang. During this time, black holes will be the only significant objects remaining, slowly evaporating through Hawking radiation, their event horizons shrinking, their temperatures rising as they lose mass. A supermassive black hole like the one at the center of the Milky Way will take 10 circumflex 100 years to evaporate completely, a timescale so vast that the current age of the universe, 13.8 billion years, is utterly insignificant by comparison. The black hole era will be dark, cold, and almost completely empty, with isolated black holes separated by distances far greater than the current size of the observable universe. The Big Rip is a hypothetical scenario that could occur if dark energy increases over time rather than remaining constant. In this scenario, the acceleration of expansion would increase, eventually becoming so strong that it would overcome not just gravity on cosmic scales, but also the forces holding galaxies, stars, planets, and eventually atoms together. The universe would be torn apart, with all structure disintegrating, all matter reduced to isolated particles, all connections severed. This scenario is considered unlikely based on current observations, but it remains a possibility, a reminder that the future is not certain, that the universe could end not in cold darkness, but in violent disintegration. The heat death of the universe is the most likely ultimate fate based on current understanding. In this scenario, the universe continues expanding forever, approaching a state of maximum entropy, where all energy is evenly distributed, where no gradients exist to drive processes, where nothing can happen. The temperature approaches absolute zero, all matter has decayed or been absorbed by black holes, and even the black holes have evaporated. What remains is a cold, dark, empty space, expanding forever, containing nothing but the faintest possible quantum fluctuations. It's a bleak vision, but it's also so far in the future, trillions upon trillions of years, that it has no relevance to anything happening now or in the imaginable future. Yet there's something peaceful about contemplating these vast timescales, these ultimate fates. The universe is patient, operating on scales that make all human concerns seem trivial. The galaxies will merge, the stars will die, the black holes will evaporate, and through it all, the universe will continue, indifferent and eternal, following the laws of physics wherever they lead. We are here for a brief moment in cosmic time, witnesses to a universe in its prime, full of stars and galaxies, structure and light. We are fortunate to exist now, in this era when the cosmos is rich and complex and beautiful. And so tonight, as you finally surrender completely to sleep, imagine the cosmic web stretching out before you, filaments of galaxies connecting across hundreds of millions of light years, voids expanding between them, the whole structure slowly evolving, transforming, flowing toward a future we can calculate but never witness. The Milky Way is falling towards the Great Attractor, carried along by currents of dark matter, participating in flows that span superclusters. Andromeda is approaching, destined to merge with us billions of years from now. The universe is expanding, accelerating, carrying distant galaxies beyond our reach, thinning the cosmic web, emptying the voids. All of this is happening now, has been happening for billions of years, will continue for billions more. And you, in this moment, are part of it, a conscious observer in a universe that is mostly unconscious. A brief arrangement of atoms that can contemplate its own cosmic context, that can look out at the galaxies and understand, however imperfectly, what they are and where they're going. Let that perspective carry you now into the deepest sleep, into the quiet darkness where consciousness dissolves and dreams emerge. The universe will continue without you, will continue its slow evolution, its patient transformation. The galaxies will keep moving, keep merging, keep flowing along the cosmic web. The expansion will continue, the voids will grow, the future will unfold according to the laws of physics, indifferent to observation, indifferent to consciousness. But for now, for this brief moment, you are here, aware, connected to it, all through the light that enters your eyes, through the atoms that make up your body, through the consciousness that allows you to comprehend your place in the cosmos. Rest now. The journey through the galaxies is complete. You've traveled from the Milky Way to Andromeda, witnessed collisions and voids, descended toward black holes, drifted through stellar nurseries, looked backward to the cosmic dawn, and glimpsed the distant future. The universe is vast, ancient, and beautiful, and you are part of it now and always, in ways both literal and profound. Sleep now, in the cosmic web, in the space between galaxies, in the flow toward the great attractor. The universe will still be here when you wake, still expanding, still evolving, still carrying out its slow transformation from simplicity to complexity and back to simplicity again. You are safe in its vastness, held by its gravity, part of its story. Sleep now, dream of galaxies. The cosmos will take care of the rest.